by commercial shipping interests to probe and overmaster the obstacles of winter on the waterways and river roads with operational assistance from the United States Coast Guard. Many of the largest and most powerful vessels in the Great Lakes commercial fleet have followed the winter run, engaged in a relentless war with ice. The shipping season has been extended for almost 2 months beyond its traditional termination date. The laboring passage of these lake carriers through heavy pack ice in the Straits of Mackinac should remind us that the name of the winter navigation game is commerce. Deep laden with Minnesota ore, downbound for the steel mills of South Chicago, the wide ice path they plow through this seaway with their blunt bows is symbolically a road of high and challenging enterprise. Ahead, off their bows, lies an uncertain future in which the health and vitality of a nation's heartland economy may well be determined by man's ability to understand and prevail against the forces of freshwater winter. And in their wake lie the turbulent rolling centuries of a continuing commerce, a commerce that has turned a vast wilderness waterway into one of the world's great routes of trade. The story of winter navigation, its challenges and opportunities, its progress and problems, belongs to today and tomorrow. Its theme, however, is most properly derived from centuries past, found in the words of Father Louis Hennepin, a Franciscan priest who shared in the 17th century experience that opened the Great Lakes interior of our continent. In the wonders of this wilderness of space and solitude, of trackless shores and vast and lonely reaches of water, he saw and recorded a glimpse of the future. It were easy to build, he wrote, on the sides of these Great Lakes, an infinite number of considerable towns, which might have communication one with another by navigation, and by an inconceivable commerce which would establish itself among them. It is this bold prophecy, 3 centuries old, that gives proper perspective to the modern laborings of ore boats in seas of ice, and a proper title to this film. For 2,300 miles along a natural staircase of freshwater lakes, the heartland waters descend step by step to the sea. Today, the broad blue backs of these linked lakes support one of the greatest flows of commerce the world has ever seen. The Great Lakes hinterland, the area in which this seaway traffic of raw materials and products finds its origin or destination, encompasses the entire continental core, 14 complete states and portions of 5 others. Through its connections with routes and systems of inland commerce, the Great Lakes St. Lawrence Seaway makes the economies of water transportation available to a vast heartland market, a market that boasts 36% of the total United States population, 42% of the nation's industrial activity, 50% of its agricultural output, and 50% of its steel production. In 1972, during a shipping season that lasted less than 9 months, 224 million tons of bulk and general cargoes were hauled on the Great Lakes and the Seaway, a total 80% greater than the 124 million tons moved through the Panama Canal in that entire year. By far the largest share of this commerce, more than 200 million tons annually, is the patterned north and south flow of bulk commodities, chiefly iron ore, coal, limestone, grain. Only water transport could carry these staples of heavy industry and heartland agriculture in the enormous volume and with the economy and efficiency required. On the trade routes of the inland seas, this transport is provided by the American flag Great Lakes Bulk Cargo Fleet. 165 carriers, each with its owner's colors banding massive smokestacks. A fleet without counterpart elsewhere in the world. Steel leviathans with high and bluntly rounded bows, hull lines long and lean, hatch tops arching flush above cavernous cargo holds, sweeping spar decks wide and uncluttered a city block long and punctuated fore and aft by tiered and towering upperworks. A design so true, so functional, that it has changed very little since the launching of the first straight-decker around the turn of the century. Coal going up, iron ore, limestone, and grain coming down. For 75 years, shuttling in constant procession from end to end of the lakes, these strong and competent ships have run the errands and served the highly specialized needs of the nation's industrial heart and breadbasket. In response to the demands of commerce, ever larger and more capacious carriers have evolved as channels and harbors deepened. Loading and unloading docks grew longer. Today, their size and cargoes are limited only by the costs of construction and by the capacity of locks, rivers, and harbors to support their loads. So closely are cargoes adjusted that on the key river channels of the upper lakes, the St. Mary's, the St. Clair, the Detroit, only inches separate hull and river bottom. To residents of communities along the shores of these rivers, the to and fro passage of the long ships is as familiar and inevitable as breathing, as well known as the traditions of excellence that have made this Great Lakes fleet world famous. Famous for navigation and seamanship, evident in the skill with which veteran officers and crews handled their ships in narrow rivers, locks, and harbors. Equally evident in the shared and instinctive ability to cope with the sudden brutality of lake storms. Famous for teamwork and efficiency, evident in the carefully planned interworkings of ship and port facilities, of dock workers and deck personnel, as immense cargoes are loaded and discharged with incredible speed. Famous for vessel maintenance, evident in constant attention to high standards of safety, and to the exacting demands of routine upkeep and repair as the fleet moves in its rigorous, non-stop seasonal schedule. Famous for provision, for the quantity and quality of select foods that grace fleet messroom tables. Meats and pastries, vegetables and fruits. Food so expertly prepared and served in such abundance as to make the galleys of the Lakes fleet the envy of ocean sailors everywhere. Captains and officers, boatswains and helmsmen, oilers, wipers, deckhands and watchmen, stewards and galley staff. The men of the Great Lakes fleet, they share also among themselves a lake's experience, a conditioning that sets them quite apart. These are men who have found their own ways of handling time, the time that belongs to their ships, finding reward and satisfaction in the skilled performance of routine duties, and the time that is their own, time to pursue a hobby, read, talk, think, relax with a game of cards. These are men who have found their own ways of adapting to an endless round-trip ritual, of adjusting to the tedium of sameness, the aggravation of a vocation that places them ever near shore, but seldom ashore for more than a few hours at a time. They're a good-humored lot, intelligent, contemplative, resourceful, individualistic. Something, perhaps a very personal relationship with the land. The lake coasts and river shores they skirt so closely, the ports they visit so often yet so briefly, has given an informal kind of shore quality to their life afloat. They eat home-cooked meals, abhor uniforms, and dress in a conscientiously unnautical fashion. Their ships, big as battle wagons, they call boats. Their profession, steamboating, and their captains, cap. They keep shore time, measure speed in miles, not knots, and a fast-traveling boat doesn't move with a bone in her teeth, but rather goes like a train of cars. And always, as pervasive as the shore, is the driving commercial nature of their calling. Their ships are named in no-nonsense fashion for directors of the company boards, and a following breeze that increases the speed of a vessel is not just a fair wind, but a company wind, making time for Uncle, the company boss. Making time for Uncle. The bulk fleet's sole reason for being is its ability to transport freight rapidly and cheaply. This involves not merely the size of the cargo, but the number of cargoes carried each season. The prime economic consideration is to keep the carriers in motion on their water highways as much of the time as possible, and to load and discharge their cargoes as quickly as possible. The predominant trade on the Great Lakes is the transportation of iron ore, a commodity whose abundance and cheapness unite to create America's industrial power. This representative iron ore carrier has a cargo capacity of 20,000 tons. Each year, in a resolute day and night race against the time restrictions of a traditional 8-month season of navigation, she will travel some 70,000 miles, making 40 or more round trips between the ore docks of Lake Superior and the steel mills on the southern lakes. During that period, this single ship will deliver nearly 1 million tons of ore. The picture of industrial vigor and prosperity evoked by the staggering volume of this lake's transport would seem surely to fulfill the promise of the good father's vision of an inconceivable commerce. On the south shores of Lakes Michigan and Erie, the fires glow perpetually in the mills. And from the north along the skein of lakes, carrying the rich harvests of domestic mines, the vessels of this remarkable fleet pass in an almost unbroken procession. Unfortunately, the picture is deceiving. For nearly 2 decades, the hard realities of foreign competition have increasingly jeopardized the domestic trade of the lakes. 20 years ago, the iron ore from the upper lakes held a major position. The state of Minnesota alone shipped 22% of the world's production. Today, the Minnesota shipments are less than 7%, primarily due to the development of competitive mines in other parts of the world. 20 years ago, there was little or no mining in Quebec, Labrador, Venezuela, Peru, Brazil, Liberia, India, or Australia. Today, these countries are all vigorous producers, and their ore deposits are typically very large and of high quality. Many of our domestic mills are buying ore from foreign mines at competitive prices. Moreover, the foreign ores enjoy the advantage of highly efficient transport in deep draft ocean vessels. On the lakes, locks, shallow harbors, and channels limit ore carriers to deadweights of 50,000 long tons. Typical ocean carriers have deadweights of 200,000 long tons. Their cargo capacity is at least 4 times greater than the largest lake ships. While the saltwater ships are able to spread their capital costs over a full year's operation, the Lakers are severely limited by the tradition of the 8-month sailing season. And it's this tradition, time-honored but completely out of touch with the times, that must give way to change now if our domestic iron mines and Great Lakes commerce are to survive. Winter comes early to the North Country, early and swiftly. By late November, streams run deep frozen from the highlands to the upper lake. New ice, undulating and compacting on the lake swells, has already begun its move outward from the shores into bays and coastal shallows. In early December, thin ice first appears in the most northerly loading ports of the lakes, its appearance accompanied by a mounting intensity in dockside activity. Bulk carriers rush feverishly to load and unload their last cargoes before the lock of ice closes the ports to shipping. Limestone from the quarries of northern Michigan and ore from the iron ranges of the upper lakes, downbound for the stockpiles of Great Lakes steel mills. The wheat of the heartland interior, siphoned off from elevator rows into cargoes for the granaries of Milwaukee and the Midwest. Coal, upbound from the southern mines to feed the stockpiles of northern industries and power plants. Through this Minnesota-Wisconsin harbor of Duluth Superior, more than 40 million tons of international and domestic cargoes have been shipped since early April. Now, in December, at loading and unloading docks, terminals and tank farms, warehouses and elevators, the cargo handling machinery of a great world port grinds slowly to a halt. Huge gantry cranes tower idly over deserted storage yards. At the base of coal and ore docks, the circulation of water through bubbler systems postpones the encroachment of ice as carriers load and unload their late-season cargoes. By mid-month, the shallow waters of the inner harbor are fast frozen. Icebreaker assistance is required to provide passage to the breakwater for the last outgoing vessels. Elsewhere, at slips and docks scattered throughout the port, other ships of the fleet observe the annual ritual of winter layup. Ladies in retirement. Shuttered, drained, all too soon abandoned, the great drab vessels restlessly abide the winter months. And here in Duluth Superior, as in other layup ports throughout the lakes, the liabilities of the 8-month season come clearly into focus. It's a harsh axiom of commercial shipping that layup means layoff. With the termination of the season, the crews of these ships join the ranks of the unemployed. The interruption affects employment not only on the ships, but in the mines, the supporting railroads, and the docks at both ends of the lakes. Because each ship's carrying capability is limited to an 8-month period, vessel operators must keep many more ships in service than would be required in year-round shipping. They must also absorb the high cost of fit-out and layup as carriers are activated and deactivated each season. For customers of the lake's fleet, particularly the southern steel mills and industries of the north, the abbreviated seasonal flow of bulk materials creates a need for costly stockpiling. The accumulation and storage of reserve supplies of coal, iron ore, limestone to permit continuous industrial operation through the winter months. The expense of stockpiling is of course reflected in the market price of iron and steel and ultimately borne by us, the consumers. For 100 years, from the time that the building of the Sioux locks unlocked the mineral wealth of the North, the tradition of the limited season became more and more firmly established. Gradually, all aspects of commercial shipping, from insurance rates for vessels to labor management relations, came to be regulated by the precedents, geared to the annual tempo of a season that closed by December and opened in April. For the iron mining industry, the largest bulk shipper, the tradition was only reinforced by the inability to handle the problem of freezing ores. The moisture content of natural iron ores caused them to freeze in railroad cars, in the hoppers at the docks, and in ships' holds. The winter difficulties of loading and discharging cargoes were insurmountable. The absence of a viable product kept the big ships frozen in their winter berths. The iron mining industry, however, was about to be revolutionized by change. By the mid-century, the iron deposits of the great Minnesota ranges, the Vermilion, the Coyuna, the Mesabi, were almost exhausted. 80 years of mining, including 2 world wars, had depleted the supply of high-grade natural ores. Within these ranges, however, there lay very large formations of taconite, an extremely hard rock, 20 to 30% of which is made up of tiny particles of iron ore. In the late 50s, the introduction of a remarkable process that could concentrate these tiny particles provided a new source of iron to replace exhausted natural deposits. Here on the Mesabi Range, huge layers of taconite are broken up by drilling and blasting operations. Electric-powered shovels load the loosened taconite into railroad cars for delivery to the plant. Every 70 seconds, an 80-ton carload of taconite is dumped into the plant's coarse crusher. Slabs of rock 72 inches thick are crushed into 6-inch chunks. In 2 further crushing stages, the chunks are reduced to the size of driveway gravel, then passed through rod and mill grinders, which pulverize the material to a consistency fine enough to permit separation of the iron-bearing particles. Because it is magnetic, this type of taconite can be run through a series of separators whose magnets capture the particles containing ore, rejecting the 2/3 waste. The black concentrate that remains is about 65% iron. Dried to a flour-like powder, the concentrate is rolled in revolving bins into marble-sized pellets. Transferred to gigantic kilns, the pellets are baked, heat-hardened at 2400 degrees. The pelletizing process facilitates handling, making the concentrate easier to transport and easier to melt in the blast furnaces of lower lake steel mills. Unlike natural ores, pelletized products, hard-baked and moisture-free, can be loaded and unloaded without difficulty in winter weather. Unit railroad trains, 100 cars or more in length, shuttle constantly between the Minnesota plants and the ports of Lake Superior. In 1973, 40 million tons of pellets were delivered to port loading docks and stockpiles for water transport to the southern mills. Since the discovery of pelletizing, the Minnesota mining industry has invested hundreds of millions of dollars in research and large modern plants to process taconite rock into high-grade ore suitable for steelmaking. Authorities agree that annual production could double by 1980. Recognition of this potential, however, depends upon the ability to meet competition in terms of cost and quality in the worldwide marketplace. The name of the game is commerce. Like their customers, the southern mills, northern pellet producers are governed by positive inertia. So prohibitive are the costs of shutdown, so critical the pressures of competition, that steel mills and pellet plants operate must operate 24 hours a day, 365 days of every year. Both industries, however, remain burdened by the need to stockpile, stalemated by seasonal interruption in the vital transportation system that joins them, the traditional negative inertia of a bulk fleet physically indisposed to move for more than 8 months out of the year. When viewed from its yearly potential, the fleet transport system suffers seriously from underutilization. On our inland seas, sheer economic necessity has sponsored, indeed forced, the first appearance of the fleets of winter. For many years, and particularly since the opening of the St. Lawrence Seaway, the benefits of an extended season have been studied by government, private industry, and commercial shipping interests. In 1970, congressional authorization of the full-scale winter navigation program propelled an all-out assault on the ice barriers of the Lake Seaway system. Under the direction of a representative Winter Navigation Board, the federal program funds and directs the specialized activities of 10 governmental agencies. The agencies are assisted by an advisory group from shipping and industry, labor, port authorities, and other non-federal units, both American and Canadian. The agencies address their efforts to the solution of major ice problems, ranging from the accumulation of ice information to a complete assessment of environmental impact. Ongoing work involves the development and testing of devices, methods, and procedures to maintain and advance winter shipping, and the determination from the study of all engineering, economic, environmental, and social aspects of the potentials and possible adverse effects of season extension. From its beginning, the Winter Navigation Program has recognized that maximum benefit to the hinterland market and the nation depends upon operating the Great Lakes St. Lawrence Seaway as a single system, a total winter waterway to the hinterland, our nation's fourth seacoast. To date, the problems of extended winter operation on the Seaway proper have proved to be more complex than on the lakes. On the international section of the Seaway, regional and city flood control and power plant needs require the maintenance of stable ice cover and balanced river flow. Methods for making winter Seaway shipping compatible with these needs is the subject of a high priority study currently underway. In the meantime, the record of winter navigation on the 4 upper lakes has been one of steady and substantial progress. In the winter of 1972-73, commercial shipping continued until February 8th, an all-time late date. The navigation season of 318 days was the longest ever recorded by fleet vessels. And in winter 73-74, late season voyages between Lake Superior and the lower lakes, lasting until February 7th, accounted for the transportation of nearly 5 million tons of cargo, an increase of 42% over the previous year.
Well, I started to work with U.S. Steel Corporation, which at that time was Pittsburgh Steamship Company. In 1929, June 5th, when I shipped out of Chicago on the Robert W. Bunsen, I shipped as deckhand of the Lake Carriers Hall with a 50-cent suitcase and $1.50 in my pocket.
Like most lake captains, this man began sailoring on the lakes in his teens. As deckhand, watchman, helmsman, officer, he rose to command, link by link, through the hawse pipe of experience. Nearly 50 years of service for the same shipping company. He is no stranger to winter navigation. For half a century, his lake seasons have begun and ended in ice. The high art of ice navigation is a polished detail in his total lakes knowledge, a requirement of command. The ship he captains on the winter run is 647 feet in length, 70 feet in beam, powered by 7,000 shaft horsepower. While not originally designed for deep winter operation, her power, quality gear, and seagoing workmanship have proved readily adaptable to the demands of the extended season. The ship is equipped with the complete weather and navigational aids. RDF, high-definition radar, gyro compass, automatic pilot, the finest radio telephones, fathometers. Her docking and locking gear is without parallel. Powerful thruster propellers are mounted in a tunnel extending through the bow. On this ship, out of ballast in dry dock, the tunnel is exposed. On a working carrier in locks and harbors, the push or pull of these propellers, swinging the bow to port or starboard, greatly improves ship handling in tight places, making it possible to turn in less space and even to dock without the use of tugs. And all the specialized attendant gear to facilitate smooth docking and locking operations. Landing booms to put men ashore to receive and handle lines. Gargantuan deck winches, big steel checking cables on steel drums. Cables strong enough to check an entire ship while going ahead dead slow. Winch controls and compressors, chocks and fairleads, bits and fenders. In each year of the winter program, vessel modifications and additions of new equipment have been made by ship owners to better crew comfort and safety conditions and to improve ice operation abilities. In the winter months, as in the regular season, the ships must move by night and day on their appointed round-trip schedules. Large mercury vapor headlights positioned at the ship's bow offer a broad, highly illuminated field of vision for night ice operation. The powerful lights enable officers to spot leads in fields of pack ice and identify the edges of broken ice channels. This blunt bow was never intended for regular ice-breaking service. Nevertheless, the most heavily powered fleet vessels have shown their ability to move through 6 to 8 inches of solid blue ice and follow a path through broken pack ice several feet in depth. Hull damage can be caused by ice pressure, corrugation of the bow shell plating, and strain damage to frames near the bow of the vessel. The results of careful strain gauge testing have produced several highly successful ice strengthening modifications. In the forepeak of this ship, being routinely inspected for ice damage by her captain, modifications include the installation of a thick concrete step at the base of the stem, an increase in plate thickness at the bow waterline ice belt level, and a decrease in bow frame spacing through the addition of extra framing units. Vessel icing is a standard cold weather navigational problem. Spray freezing on contact with decks and superstructure can swiftly add many tons to the weight of a vessel. In ballast, her cargo holds empty. This 1,000-foot barge could compensate for severe ice accumulation by shifting of ballast while underway. For the barge, ice buildup still constitutes a distinct and costly nuisance. Frozen cargo hatches represent lost time and money at the loading docks. The looming forward superstructure of the conventional laker offers a substantial shield against excessive spray. On the decks, hot water under pressure is used to combat ice buildup in its early stages. Trials on the winter run have demonstrated the further protection afforded by strips of weather cloth. Installed to intercept spray on the fence rails of the spar deck, the cloths have greatly reduced ice buildup around the forward hatches. In the long tunnels connecting the forward and after sections of the vessels, high-powered modine heaters are positioned to provide maximum warmth. On some ships, crew comfort has required the insulation of deadlights and bulkheads. Plexiglass storm windows have been installed on all outside portholes. And in pilot houses, the installation of heated windows and windshield wipers permits a clear vision under the most extreme icing conditions. The use of VHF radio telephone equipment increases the fidelity and reliability of the ship's safety communication system. Crew safety receives maximum attention. Highest program consideration is given to experimental testing of survival equipment by the Coast Guard under cold and heavy weather conditions. This life raft, being stowed in a protected but accessible area on the forecastle deck, will fully inflate within seconds with the simple tug of a lanyard. Its inflation capacity was confirmed by prolonged testing in snow and ice at sub-zero temperatures.
Okay, John, let her come right.
Got it right, sir.
And let her swing like a button on a hen house door.
Here you go, sir.
After the freeze-up of Duluth Superior, the center of shipping activity shifts to year-round loading ports on the northern lakes. With the warm, shared informality so characteristic of Lake's command, the captain orders his ship through a 180-degree turn into the wind, making his approach to Two Harbors, Minnesota. Situated on a deep-water landlocked bay and safeguarded from superior storms by great ridges reaching out from the mainland, Two Harbors is a principal port for the loading of taconite. So efficient is the winter loading operation that this ship, docking at 9 o'clock in the morning, will be fully loaded with 20,000 tons of pellets and underway downbound by 1 o'clock in the afternoon. Dumped directly from railroad cars into storage bins on the high docks, the taconite awaits the arrival of vessels at any hour of the day or night. Streaming down the long chutes into cargo holds, the roaring flow of pellets is controlled by locking gates as the ship is shifted at the dock to receive a balanced load. In the middle of December, the large, relatively motionless bodies of water in the St. Mary's begin to freeze over. The first traces of ice appear in the connecting rivers of the lower lakes. Through these early stages of formation, the fleet operates without assistance, but by the end of the month, the ice begins to restrict vessel movement. On the upper lakes, the physical impediment of ice to winter shipping is most severe in the connecting channels. The St. Mary's River and the Sioux Locks between Lake Superior and Huron, the Straits of Mackinac connecting Lake Huron and Lake Michigan, and the St. Clair and Detroit rivers linking Lakes Huron and Erie. On these connectors, the work of preparing for the extended season begins long before the onset of first ice. In the fall, here on the St. Mary's and on southern rivers, Coast Guard tugs and buoy tenders remove regular season buoys from their channel positions. Summer buoys, the standard black cans and red nuns, are unreliable navigation aids in the winter months. Overmatched by the savage force of ice and river currents, they are often damaged, dragged completely out of sight beneath the mounting ice sheet, or pulled off station to become false aids. By late November, all but the most important summer buoys have been withdrawn to storage yards at Coast Guard stations. In the same yards, the specially designed buoys of winter navigation lie ready for placement. In a variety of shapes and sizes coated with high visibility paint, these experimental ice buoys, lighted and unlighted, are being tested for use at crucial channel junction and mid-channel positions. 3 years of trial and error experiment have produced these successful prototype designs. Broad-based for stability in moving fields of ice, their light spires encaged to prevent the toppling weight of ice and snow. The buoys are held in position by stato anchors, weighing nearly 5 tons, and designed to dig deeply when subjected to strain. Placement of the experimental buoys and their anchors is arduous and exacting duty. The slightest mistake could cause serious injury or vessel damage. Working with heavy equipment in numbing cold, crewmen ready a junction buoy for drop. 32 feet long and 9 feet in diameter, this monster is painstakingly jockeyed into position by the crane operator. Its stud-linked chain flaked for run-out on the deck. The great anchor, held by a chain stopper, already hangs alongside, awaiting release. The channel location must be pinpointed exactly by cross bearings before the release signal is given. Light blinking and soundly moored, the buoy rides at anchor. Within a few weeks, entombed in river ice, she will remain upright, unmoving, and functional, marking a vital channel turn for the winter fleet. Other winter navigation problems on the lakes and their connectors have created the need for all-weather navigation systems to supplement the conventional aids of the normal shipping season. During the winter, shore aids and channel range lights become obscured by snow and ice fog. Ice ridges along shorelines cause ships' radar to project distorted images. To solve these problems, a variety of new navigation aids have been developed and tested under the supervision of the Coast Guard and the United States Maritime Administration. This device, called a Raycon, is a radar beacon designed to transmit a coded signal to the radar screen of an approaching vessel. Installed in critical river and straits locations, Raycon signals can be received by vessels at a distance of 12 to 15 miles. The coded target that appears on the radar screen indicates the bearing and range of the vessel relative to the Raycon's position. Increasing success with Raycon during the winter program led to the initial testing in the winter of 73-74 of a combined laser and radar system operable under all visibility conditions, including heavy rain and snow and dense fog. Aboard a fleet vessel, this technician has begun the installation of the sophisticated equipment, which will include laser and radar transmitters and receivers and a computer control console. Depending upon weather conditions, either the laser or radar system works in conjunction with reflectors positioned along the shore sides of channel passages. A display console mounted in the pilot house gives the ship computerized speed data, measuring its distance from the center line of the channel and from the next river turn. Advanced ice navigation preparation by the Coast Guard and other agencies is matched by the work of the Army Corps of Engineers in the fields of ice management and control. From March until December, the hard-working hopper dredges of the Corps work the exposed coasts, rivers, and busy harbors of the lakes, maintaining the required depths of navigable waterways. As the lead agency in the winter navigation program, the Corps has involved its dredging vessels in critical duties to facilitate shipping. In the St. Mary's River during the normal season, all upbound and downbound vessels make use of common channels, except in the area of Navigational Island. Here the channel divides. Upbound boats coast the eastern shore of the island, downbound the western. During the winter season, the western route is closed to shipping to permit the residents of Navigational Island access to the mainland. All traffic, upbound and downbound, must negotiate the slow bends and sharp turns of the eastern channel. Although one half of this channel is dredged to 27 feet, the outer half is only 21 feet deep. A laden vessel must remain well within the 27-foot channel. On the sharp turns, the vessel bow must hug the inner channel edge to provide room for the wide after sweep of the turning ship. In river steamboating, the front end must always be well aware what the hind end is doing. As river ice thickens, however, and the ship track becomes filled with slush ice, it is increasingly difficult to keep within the deep channel on the turns. Corps of Engineers ships, by pre-season dredging of the 21-foot channel shelf, have widened the shallow corners of the sharpest turns, permitting more room for maneuvering and greatly reducing the hazard of grounding. The winter season has been extended not only by modifying vessels to cope with the ice, but also by modifying the ice through which the vessels must move. During the first 2 years of the program, a 3,000-foot air bubbler system was installed by the Corps at this difficult Lime Island turn in the lower St. Mary's River. Buoyed deep beneath the surface, the long bubbler line facilitated ship operation in the turn area by circulating warmer water upward from the river bottom to limit surface ice thickness. Success with this experiment has contributed to the current research and development of a more extensive system for Duluth Superior Harbor. Another ongoing experiment performs the hat trick of combining both vessel and ice modification. The delicate machinery being serviced here aboard a lake carrier is a compressor system that pumps air to a bubbler attached to the ship itself. Pumped through the orifices of long pipes extending below the waterline from bow to stern quarter on both sides of the ship, the air envelops the vessel in a thin coating of air bubbles. Intended to reduce friction on the hull in slush ice-filled channels, the air coating system is being subjected to rigorous efficiency tests under varying ice conditions. Charged with the management of the world's busiest locking service, the Corps has succeeded in providing continued operation of the Sioux locks, consistent with the expanding needs of the extended season and the harsh demands of maintenance. Ice interference with lock operation arises from masses of drift ice being carried into the locks by the blunt bows of the downbound vessels, and ice buildup on gates and machinery resulting from repeated immersions. The current use of valve flushing and bubbler systems to combat restricting ice has kept lock gates functioning under extreme winter conditions. In winter 73-74, delay time in commercial ship performance was reduced by provision of 24-hour lock operation until early January. The ice constrictions on the connecting channels also accentuate the impact of winter navigation on the environment. The most significant problem has been the intermittent interruption of ferry service to the mainland for residents of Sugar Island on the St. Mary's River. The ferry has been repowered, structurally strengthened, and modified by the Corps of Engineers for operation in ice. Twin bubbler systems, one remotely operated from the ferry, have been installed to control ice formation in the mainland slip. For the greater part of the 73-74 extended season, the rugged vessel provided regular service through the ice-covered channel. In mid-January, however, the routine passage of lake carriers breaking the newly refrozen ice cover above the ferry crossing caused the broken pack to float downstream, jamming the crossing and smothering the bubblers in the slip. Consequent impairment of the ferry and interruptions of service required emergency transportation assistance from the Coast Guard. The concern of government and commercial shippers sponsored an immediate study of ice control measures to solve the ferry problem. Less comfortable but more successful mainland transportation has been provided by the Corps for the winter residents of Lime Island. A propeller-powered ice sled, similar in design to a Florida swamp airboat, is used to negotiate the vessel track that lies between the island and the shore. In the hands of a skilled driver, the craft skims swiftly across the smooth, fast ice that edges the channel track. Literally leaping into the channel, the sled, pitching and jolting, threads its way through and over the ship-tossed ice ridges to the opposite edge. Comfortable it isn't. Functional it is. The machine gets the job done, and the experience is memorable. Throughout the lakes, rivers, and harbors of the Seaway system, the Winter Navigation Program has brought modern technology and teamwork to bear on the winter mystery of the lakes. The variety of the integrated research effort is reflected in routine work in progress in the area of the St. Mary's River. In Lake Superior, aboard a carrier downbound for the Sioux, a technician ejects instruments called bathythermographs into the lake waters to record a water temperature profile that will provide data used in forecasting ice formation and breakup. In the river, aboard a Coast Guard tug, researchers regularly measure the thickness of brash or slush ice in the vessel track. Others measure the thickness of fast ice and snow cover along the river shore. At critical channel sites, the possible impact of the extended season on shore erosion is photographically assessed. And elsewhere, environmentalists compile a continuous photographic record of selected dock and shore structures to determine the effects upon them of moving ice before and after ship passage. Ice formation and growth on the entire river system are documented weekly by aerial photography. Ice charts and mosaics resulting from these photo flights are transmitted for use in ice forecasting. On the fast shore ice, a team of cold weather research scientists measure the force of ice on pile structures by using a portable hydraulic cylinder to push a vertical pile horizontally against the ice sheet. Bit by bit, item by item, the results of these and many other diverse studies conducted simultaneously throughout the waterway system are creating a scientific mosaic of Great Lakes and Seaway winter, teaching man more than he has ever known about freshwater ice, its growth and development, its movement and decay, its management and control. Other program agencies look to the future, sponsoring long-term evaluations of the technical and economic problems of the ships of winter commerce. At the University of Michigan, a computer program has produced a procedure for estimating the profitability of a ship operating in extended season trades. A portable computer can be carried directly to the offices of interested ship owners, shipyards, and designers. Programmed with the specifications of a ship already in service or planned for construction, the computer gives a complete range of estimates for the vessel's extended season revenue potential, with alternatives for various periods of extended season operation and various lake routes of trade. Since 1970, the retirement of older American flag carriers has reduced the average age of U.S. bulk vessels in the Lake Carriers Association from 45 to 41 years. The stress of competition and the promise of a longer navigating season have already stimulated a flurry of shipbuilding, with the trend towards larger and larger ships, provided with self-unloading capacities and carrying 60,000 tons of cargo. In recent years, 7 new large vessels have appeared on the lakes. Shipbuilders contemplate the building and use of ships 1,100 feet long, fully strengthened for ice operation. On the design tables of naval architects, in water and ice testing tanks, the designs and models of the long ships of the future are already taking shape. Ships with bold new dimensions, larger, faster, more efficient, able to move the staples of industry and agriculture for 12 months of the year, able to compete with foreign carriers and keep America's ores competitive with foreign producers. By the year 2000, it is estimated that almost half of the bulk cargo fleet will be in the class of supercarriers, 850 to 1,100 feet in length. In the meantime, as this new chapter in the story of lake transport unfolds, the success of winter navigation continues to depend upon optimal utilization of two key resources, the men and ships of the American flag fleet, and the operational support of the Corps and the Coast Guard. The most extreme ice conditions on the upper lakes and their linking channels are encountered on the crucial winter route that runs from ports like two harbors at head of the lakes to southern Lake Michigan via the St. Mary's River and the Straits of Mackinac. By January, thick ice coverage usually extends from Whitefish Bay down through the entire St. Mary's to upper Lake Huron. High winds on Lakes Huron and Michigan force ice into the arc of the straits. Pack ice, thick and pressure-ridged, can be anticipated on the 40-mile stretch between Round Island and Lansing Shoal. At the period of maximum coverage, only 17% of the trade route is ice-restricted. The balance, 83%, is normally ice-free. On Lakes Superior and Michigan, the ships operate for the most part in open water. For lake captains confronted always with the threat of adverse weather, the word open needs qualification. In the regular shipping season on Lake Superior, for example, the protecting lee of a northern or southern shore, the buffering arc of the Keweenaw Peninsula, offer refuge for vessels from seasonal wind conditions. In the average winter season, broad formations of consolidated shore ice and close or open pack cover many of the coastal stretches, reducing the area of open water. Deprived of room to run and places to hide, captains must anticipate more direct confrontation with the elements. The safe maneuvering of fleet vessels to minimize ice buildup and the potency of lake storms requires consummate seamanship. It also requires the fullest possible foreknowledge of ice and weather conditions.
All stations, all stations, all stations. This is the United States Coast Guard Group, Sault Ste. Marie, Michigan. Coast Guard Marine.
In addition to regular Mayflower and lake weather bulletins, lake carriers are supplied at frequent daily intervals with timely weather and ice observations from the Coast Guard's Ice Central headquarters in Cleveland. At Ice Central, input is received from fleet vessels, from National Weather Service remote stations, and from Coast Guard ice reconnaissance aircraft. Ice summaries, outlooks, and forecasts, and special marine weather bulletins, compiled and analyzed by headquarter experts, are disseminated to Coast Guard control stations for transmission to ships. Refinements in long and short-term forecasting techniques developed during the winter program have increased efficiency and safety in fleet operations. Another valuable ice information tool used in the demonstration program is an aerial mapping system developed by NASA to provide ice coverage information on a real-time basis. Observation planes equipped with the odd-looking paraphernalia of a system called side-looking airborne radar make daily mapping flights over the lakes during the winter season. Sensitive image recording equipment employs radar microwave radiation to penetrate the most severe weather conditions and map areas of lake ice coverage many miles in width. Ice conditions on all of Lake Superior can be radar filmed in a single round trip over the lake. Images recorded in flight are developed in mobile units at airfields where the planes are based. At the units or at Ice Central, the ice condition information of the developed picture is interpreted on a matching chart. Both the original picture and the chart are sent by telecopier to stations which transmit them to ships via radio telephone. Within a few hours after a flight, ships plying the Great Lakes routes of trade are in possession of a detailed, real-time breakdown of all ice conditions in their immediate and general areas of operation. Inevitably, in Whitefish Bay, the St. Mary's, and the Straits, the work of winter navigation comes down to push or shove. Men and ships and the gritty business called cutting ice. In the early hours of a January morning, a downbound carrier moves through loose and broken pack in Whitefish Bay. A southerly wind has shattered the ice cover, driving the pack north into the waters of the open lake. The ship negotiates the bay passage without difficulty. By midday, however, the ice situation has changed radically. Jammed together and driven by prevailing northwesterly winds, fields of solid blue and newly formed lake ice have drifted south, completely covering the bay and clogging the funnel-like approach to the Sioux. In this exposed area, as in the Straits of Mackinac, the swift and whimsical control of winds and currents over massive bodies of ice presents a rigorous challenge to Laker captains. The watchwords of ice navigation are patience and prudence, the cardinal rules to keep moving and maintain freedom to maneuver. The ice of the Straits is constantly in motion. The path of a previous vessel, only an hour or so old, is a totally unreliable navigation aid. Whether operating independently or in convoy, ships navigate by radar. Endeavoring always to work with, not against, the ice movement, captains and officers keep a watchful eye for leads in the pack. Windroad areas where ice has piled and thickened into pressure ridges are given the widest possible berth. Excessive speed increases the risk of ice damage, but the ship's propulsion plant and steering gear must be capable of fast response to maintain headway and control of the ship. When a ship in ballast becomes beset, she can sometimes free herself by pumping and transferring ballast from side to side. Laden ships stopped in their forward progress can back off, moving cautiously astern with rudder amidships to protect vulnerable propellers. Often they are able to regain sufficient forward motion to break through an ice impediment. Once truly trapped, a ship is at the mercy of the ice. She goes where the pack goes. Swift icebreaker assistance is needed to keep her from being driven onto one of the many shoals fringing the Straits seaway. Of the extended season methods tested and applied to reducing or removing ice cover in navigation channels, use of icebreakers remains the most available and flexible of all winter navigation resources. In winter 73-74, an icebreaker fleet of 5 vessels was deployed to assist commercial navigation in the St. Mary's and the Straits. The cutter Mackinac, queen of the fleet for lake ice-breaking service, 292 feet long, 75 feet in beam. Her diesel-electric power plant producing 10,000 shaft horsepower. The South Wind, a polar icebreaker comparable to the Mackinac in size and power. The versatile 180-foot buoy tender Sundew with 1,800 horsepower. And 2 smaller multi-purpose harbor tugs, the Arundel and the Naugatuck, 110 feet long, driven by 1,000 horses. The round-bottomed icebreaker operates by means of sheer power and crushing mass, its bows designed to climb and bear down upon the ice sheet, breaking it by weight. Broken ice passing beneath the vessel is further fragmented by the suction, impact, and thrust of the propellers. Moving at high speed through ice flows that can be broken and pushed outward by the surging action of her stern wave, a conventional breaker can create a track greater than twice the width of her own beam. In the ice passages of the river and the Straits, power and mass become the instruments of the world's most sophisticated ice-breaking science. By January, commercial vessel operation on the St. Mary's is confined to a slender serpentine channel track hemmed by deep and fast river ice. Pulverized by continual ship movement, the ice of the track proper becomes brash, a mixture of slush and pieces of broken ice, building to greater and greater depths. Cohesive and resilient, the brash clings to vessel sides, making passage extremely difficult. At depths of 6 to 8 feet, brash can completely stop an average-powered laker. At river narrows, where jam-ups of brash ice occur most frequently, the Coast Guard cutter Mackinac chews a deep parallel relieving cut into the fast ice lining the track. The subsequent passings of carriers will force the brash outward from the track into the cut, diminishing the depth and consolidation of the slush. Subject to sudden weather and temperature shifts, ice conditions on the river change rapidly. Facilitation of ship movement requires regular maintenance of the track along the river's entire 40-mile course. Standard procedure for maintaining track width sends the larger cutters down the channel sections at the highest speed consistent with river regulations. The resulting crushing and churning action of bows and stern wave weakens and fissures the fast edges of the track. This procedure, called wake breaking, is followed up by the harbor tugs, the tough little terriers of the Coast Guard fleet. Backing and ramming, they attack and break up the fissured ice, restoring the required width of the track. The maneuverability of the tugs is also ideally suited to corner cutting, maintaining proper turning space on the sharp channel bends dredged by the core. The tug arundel cuts a slice through the fast ice on the outer edge of a Nevish Island turn, alternately backing down, then ramming forward over the area between the initial slice and the track. The intervening ice is reduced to smaller and smaller pieces. Providing preventive icebreaking and escort service on 4 lakes simultaneously has placed a severe strain on the capacities of a Coast Guard fleet limited in the number of its vessels. Proposals have been submitted for additions to the fleet in the near future of several small but highly powered icebreaking tugs. Meanwhile, the Coast Guard, like the ships of commerce, serves the needs of navigation, and brilliantly with the fleet that is. The extended season program has delegated to these winter fleets the most important single economic undertaking on the lakes since the building of the Soo locks. Much has already been accomplished. Within a surprisingly brief period, a 10-month navigation season has been achieved. The myth of the 8-month season has been laid to rest once and for all. Much remains to be done. The building of ships, improvements in ice technology, continued betterment of safety and survival equipment, ship's officers to be recruited and trained, an effective system of crew relief to be established, environmental and people problems to be solved. Commercial shipping and the agencies of government are squarely committed to direct action in these and other related areas. Close at hand now lies the realization of year-round navigation, the key to a commerce that will affect the prosperity and well-being of uncounted millions of Americans. For lake and seaway trade, for industry and agriculture, for the heartland market and the national economy, the anticipation of gain is near and enormous. Going like a train of cars, the vision of an inconceivable commerce rides like a bright promise with the fleets of winter. Fleets confident in their readiness to meet the challenge of today and grasp the great expectations of the future.